Thank you, Julius, for a very nice introduction. I was very curious how you what you would say to my talk, because I gave Julius my slides before that, and I think they are quite hard to decode what I want to say to this. So I think you made quite a good job. I would like to talk about declarative visualization. I have been working in the field of scientific visualization for some time already, and I like to add some adjectives which augment the original meaning of the visualization into a certain direction. And it's true that I have been working on illustrative visualization before. Now I would like to bring the goal of visualization a little bit into the foreground more explicitly by stating this adjective declarative. We know from programming that there are different forms of programming. There could be a more imperative way of programming certain procedure, or there could be declarative ways of defining what we want to achieve rather than how to get there. And along these lines, there is an analog that sometimes we are more performing certain visualization in an imperative manner, which is strictly state what should be done, and at the end we have the result. But we can also be inspired from the programming languages field and try to make the visualization in a more declarative way, so goal-oriented. And what could be the patterns in order how can we formulate this goal orientation that will be the topic of my talk. So this is a short outline of the talk, which will be explained in the next slides. Traditional visualization, I would like to start in a very critical way. I don't mean it critical, but in order to make my point, I think it's good to be very polarized. Things are not black and white, but sometimes to explain a very conceptual differences, it's good to make it a little bit more black and white. So sometimes in the visualization community, I had the feeling that the visualization pipeline is oriented from data to the display, actually, not even to the viewer, and people are concerned with well, we have this volumetric data set, and let's do something with it so that something is shown on the screen. And stating the question, like, what is this data set actually showing? What is needed to be explored in this data set? These questions which should be asked in the first place have not been asked. And I think it's partially because we are in the visualization community often technologists who are fascinated by the technological aspects of visualization and are a little bit weak to be oriented on the questions which are maybe, in my opinion, more fundamental in driving visualization. So, and you can see it on the pipeline, visualization pipeline, and this is with small changes always the same. It starts with a data acquisition, and then there are certain processing steps, and then it's displayed, and often it ends here. Recently, people started to realize that the situation is not that the visualization ends on the screen, but there is further, the pipeline continues on the human side through different stages, and finally it reaches certain cognition where hopefully some insight is generated. I think it's quite useful to separate visualization challenges or stages into three parts. One is this data-centric stage, where we are typically dealing in visualization with, for example, out-of-core situations where our dataset is so large that we cannot have it in our main memory at the same time, or we have a streaming situation where huge amounts of data are coming into play and we need to process it somehow. People are working on this, and without this work, we cannot really proceed further along the pipeline. It's a very important stage. Another important stage is computation-centric stage, where we are more concerned with making things fast. And certain algorithms have been ported to, for example, GPUs in the previous decades, which allowed suddenly, let's say, direct volume rendering to be performed at interactive frame rates, and suddenly no pre-processing is needed. So that is the second stage, and the third stage, which I would call, is the user-centric stage. And there I also allow myself to include this visual mapping, because when we choose a visual metaphor, we need to kind of relate it to the user. We cannot do it without it. I think in this imperative approach, where we just get some data or the data is thrown over the fence on us, and suddenly we have this engine block data set, which is a volumetric data set. We have no idea what is there, what should be shown, but we still show our visualization technique on this data set without having any clue what insights should be in this data. So this is the setting, and I am concentrating a little bit more on this user-centric stage in my research. If we look at maybe traditional direct volume rendering, which I would say could be misused in this imperative way, that we just use this technique and not knowing whether it's useful or not, we might end up in such a visualization. This data set, after it has been analyzed by a doctor, there have been certain areas marked as potentially interesting to communicate. Despite this fact, and which is a pathology between right kidney and the liver, despite this fact, none of these things is really shown. We are seeing a skin, which would be completely irrelevant in the clinical scenario to look at from this particular scan. We are looking at the bone structures, and then we are looking at some kind of a combination which shows the soft tissue and the hard tissue as well. In addition, if you look at this animation, you sometimes realize that it's rotating one direction and suddenly another direction. It has some kind of a perceptual problem, at least I experience it. So it's often, very clearly, there has not been too much concentration on what is the intent and how the viewer processes the visual information, because there is some perception disharmony, and also the intent is not present here. Typical imperative systems have a huge amount of parameters which people can play with, and like, for example, transfer function. It's a very generic methodology, and sometimes it's necessary to use such a methodology, perhaps in some scenarios, but in some scenarios it's not, because there is already enough of information to specify the visibility of certain structures which needs to be shown. So the first pattern was about, which now has just left the slide, was about that the data, it's linked kind of, the information is going from the data towards the viewer, but the viewer is just like an enforced observer of what is going on. The second approach maybe could be that the information comes first from the viewer toward, and it's processed, and finally it reaches the data which he wants to look at. And this kind of speculation is motivated by the fact that visualization, we have to understand it as an enabling technology. It's not that we like to do it and therefore it is here. It's because somebody else needs it, and therefore we are also our research is supported, and that the goal is to provide insight of information which is more difficult to extract otherwise, where the computational methods fail. So, for example, if we can solve if we can answer certain particular question with a non-visual form, automated processing, where we get the information out of it, which is necessary and relevant for the domain, then we should not show the visualization. We should just use the computational power to give us the answer. If this is not possible, and we are part of this computational engine and using our perceptual and cognitive capabilities to find the answer, then visualization should be used. But then also, the visualization has to be aligned with our perceptual and cognitive capabilities to find the answer quickly enough or find the correct answer. So, and there are usually along to get to a certain goal, which is sometimes an iterative process, there are certain tasks which the user does in order to reach this goal, this insight. However, if we know the domain scenario, we should allow just for this interaction metaphors, and probably not for other ones, or simplify them, constrain these interaction metaphors in such a way that the user does only what he should do and is not disturbed by other type of functionality. For example, limit the amount of parameters to a minimal set. So I would claim that from as this is visualization is an enabling technology, there is nothing like a generic visualization pipeline. Every problem has to be treated differently. Every domain has maybe a different metaphors which work the best, but still we can talk about certain common patterns. And I would claim that the most present pattern which is in visualization is that there is a visual dialogue between a machine and the human. And we are often interfacing through the machine certain kind of data. But the data is often understood as it should be measurements, simulations at the most. The data could be some models which are extracted from measurements. It could be already abstracted information. It could be even mental representation, where an author of a visualization is the user of the visualization at the same time. And visualization is the part of a visual thinking iterative process. So I would like to stress that the goal is the only reason for visualization to exist. And therefore, if the goal is on the side of the user, I'm suggesting that the user should be the one where the visualization starts. But then when I thought about this, of course this is utopistic, because at the end the information is stored in certain data form, and this information is going towards the user. So it's not going the other way around. So we are still the information flow is aligned with the visualization pipeline. But maybe we can build up in the yeah. So this one where the data is at the first place, probably we are forced to use such a pattern, but perhaps there are certain mechanisms where we can bring the user more into the game, not just at the end he's staring at the final information. So we have been also working on imperative, strictly speaking, imperative techniques, which didn't have the declaration as the main aspect, but we were at least looking at what have illustrators done. What they have done is cool, looks nice. Perhaps we can do it too, and probably it will be good as well, because the illustrator's work was good. And as Julius said these words, we were literally mimicking the techniques of illustrators and tried to make them interactive. And in some sense, we brought the small declaration aspect into the visualization, because at least now, when we already have this information, what is interesting for the viewer, we can modify the rendering technique in order to give visual prominence to the structure of interest, which is this yellow spot between the liver and the kidney. So still an imperative approach, and we didn't ask too many questions how because This cutaway views, which we see now, is an evolutionary process. The illustrators started to work on this, and they finally ended up in some local optimum of the illustration technique. And we are now trying to mimic their approach without knowing through what stages this technique came through. And there are many drawbacks which is in this naive approach. You can see certain flickering. Your eyes will probably not be always focused on the structure which is important, but sometimes the flickering will force you to look somewhere else, and this is not intended. So there are many things which have not been considered. The mimicking was not perfect. Maybe sometimes it's useful to look into the visual literature and be inspired by visual perception in order to consider it in the development of your visualization design. That we partially did that in our work, which has been presented at this place last year by Andrea Lidau, where we used the concept of cutaways on visualization of geological structures, which are enclosed by geological layers. And the result was this: the approach of creating the cutaways just didn't deliver any meaningful message. And there we realized that there are certain design principles which can drive the creation of the cutaways, as for example making the cutout a simple form which is distinct from the forms which are in the data, so the cutaway is never misinterpreted as a part of data. That we include sometimes some relevant information into the cut, that the box cutaway is not a strict enforcement but can be overridden. That there are enough of depth cues so you can understand the depth relationship, and that there is certain static information in the cutaways, like for example here on this video, where the cutaway is view independent as it is possible, and in situations where we will read suddenly the structures inside will not be visible, the cutaway is redefined. This allows you, in the previous case when there was this cutaway all the time created, you didn't have a kind of a good reference. You couldn't relate the wall of the cutaway towards the part which was inside, because the wall was constantly changing. So now it is not changing, and you can by motion cues, for example, infer the depth of the structures inside, which are channels within some geological bodies. Okay. Another work which was where we tried to alleviate the user interaction, where we tried to constrain it. If we have a scenario where we want to answer basically a question, show me this and this object, well, we have two choices. We can either just present this data and the user can rotate himself from one viewpoint to the other, which for people who are not used to interacting with 3D scenes might be quite tedious. Instead of, we can just show the structures which are part of this data, and the user can click on the structure he is interested in, and he can be automatically navigated to a good view which conveys the structure well. So that is maybe a good plan, but if we look at how it was created, then we realize that we are computing some characteristics, like how far are the objects from some viewpoint in order to classify the viewpoint quality, how visible is the structure, how much the structure will be projected to the center of the screen, and all this has been plugged into some information theoretic framework, and that evaluated the best view. Well, where is the viewer here? He was not considered at all. So we considered his possible goals. He might want to see the visualization in a quick way and be navigated in a pleasing way from one viewpoint to another. But then when we realized, when we designed the visualization technique, we just did it without the user entirely. The person, the human, was not part of the visualization design. It was some computational machinery. And we also don't know whether it works. We actually never asked anyone whether it's pleasing. It was only our own intuition that this works nice. Which brings me to another point where evaluation of your visualization design is one way how you can bring the human into the visualization design process. For example, like on the work where the volume visualization has been recently enriched by global illumination effects, as for example shadows and so on, which has been shown on the volume data primarily because we could suddenly. The computational machinery was fast enough that on volumetric data we are able to show approximation of global illumination. Whether it is good or bad, this was not the first question we have been asking. And sometimes it's good, but the goal, visualization researchers should have the goal always in the mind in the first place. While we did that, and compared to foam shading, we indeed receive good more depth cues into the scene, but at the same time, we introduce some information hiding. Visualization should maybe in some scenarios it should be about hiding information, but primarily it should show information if possible. So the shadow has a disadvantage, which means that it hides certain shape, and it might be relevant in certain scenarios. Here I'm showing it on a data set of a heart, which nobody basically told me that the shape of the heart is now the key question in the diagnosis. But so this data set was also thrown over the fence on me, and I'm just demonstrating the technique on it. So, but if given that on volumetric data set the shape information is of relevance, and also in the areas of shadow, we can either modulate the shadow so that it's not that prominent, it's not black, or we can have the same contrast amount, but the contrast is not distributed only along the luminance axis, but is also in the part of the chroma. By that we create some shadows which are chromatic, and it's often used also in illustration in order to convey that structures are in shadow while still being able to see the shape which is in the shadow. So we have developed a technique which was creating these chromatic shadows. And finally, we evaluated it whether it makes sense. So the evaluation consisted of several stages. And we basically wanted to answer two questions. When we have chromatic shadows as a visual metaphor, the chroma information, will it reduce the depth perception, or whether the depth perception will be untouched? That's one question. And the second, is the shape in the shadow more perceivable than with the luminance information, and how it also relates to the foam shading, where no information hiding is going on. The principle how we did the chromatic shadows, we wanted to keep the same amount of contrast. So if you have here an object color, and this will be the color of the same place on the object after the shadow is casted there, let's say in a photorealistic rendering scenario. So, and then we looked at the contrast difference of these two colors in a perceptual color space, and we were basically keeping the same distance, but moving the color which should be chosen for the shadow representation in the blue part of the hue. And here you can see the relationship between this S0 to S5. How does this look like on a synthetic scene. So you will probably believe me that here the shape perception task in the shadow will not be performed too well, while probably here people can understand the shape better without making this test. It somehow looks that as it could be the case, but we also can see somehow that the scene looks a little bit flatter. It's not so, we do not see the depth as well as in the case S0. So there is for sure some kind of a compromise which needs to be made. For the shape perception task, we use this gauge figure task suggested by Jan Koendering and his colleagues quite some time ago from the vision science, where you basically place just this small ellipsoid and normal to this ellipsoid on the small surface patch, as you think that the normal would be pointing out from this shaded surface. So that is the task, and it is quite an intuitive task and very simple, I believe. And we have seen that the error of placing this gauge figure was in the case S0 the highest, and then it was more or less there was still some error, but the error was smaller. So we definitely have seen more shape. The experiment is confirmed that. Then we had a depth task, which we also conducted, and here we see the three scenarios which we tested against. So one is just the funk shading, where we have a assumption that not too much depth cues are present. Here is our chromatic shading or shadowing, and the last case is the occlusion shading model, which provides in our assumption most of the depth cues. And we performed a task where it was basically a relative depth perception task, where we had 3 points. We had the red point, blue point, and the yellow point. And the question was, where in the depth is the yellow point in relation between the red point and the blue point? Is it between them? Is it outside them? And also you can define to which one it is closer and to which one it is more far away. With funk shading, the error was much higher than with the optimal case, which was the global illumination approximation, but our chromatic shadows were not performing too badly. So I'm telling this story because I want to show you that there is a possibility to evaluate how your visualization technique performs, and we have seen that we can find some compromise which conveys both the shadows and for the depth cues and also the shape information. But that we were lucky that we have chosen visual encoding which was improving the situation. It's very legitimate to choose a visualization metaphor which will not do it. So it could be, the outcome could be positive or negative. So, and what can we do when the outcome is negative? That's very bad, right? We have new visualization system. We have made a half a year project, and then at the end it's worse than what we compared it against. Well, it's not negative. You just have to. It's not so bad. You just have to change your visualization design and evaluate it again, right? Well, a lot of work, one could say, but negative result is also moving you somewhere. It tells you that this way it's worse. Go probably the other way. So it's kind of it's information still. I'm in between placing one pattern where the user can be part of the design process, but where the system is iteratively performing evaluation of the visualization design, whether it satisfies the intention, and once this design is good enough, it's shown to the viewer. That is also a possible pattern if we have a good model for the good model of the user, of his perception or of his task and so on. So given that we have this hypothetical scenario that we have a good model of the viewer, then we do not need to bother the viewer by evaluation, because the model can evaluate it for him, and we can in iterations come to some optimal visualization. That's also an option. Some time ago we did that, but without the model, but which would be just based on some visibility condition. So it was not perceptual. It was again, I would say, data-centric, but that was kind of then maybe an early bird on self-evaluating the visualization in a loop. The task was we have some initial transfer function, and we would which is showing in dominance the seeds, and we are not so interested in the seeds, but in the pulp or in the skin of this orange. Therefore, we would say we would like to have the distribution of visibility in such a way that 25% of the ring will be visible, pulp will be visible 0.6, 60%, and the seeds by 15% only. And we are changing the transfer function in such a way that the visibility of these objects is finally corresponding to these ratios, or is as close as possible. Well, the human was not in the loop, and there was not a model of a perception. There are recent works of the group of Van, for example, where they evaluate in this kind of an iterative manner, where they have a model of depth perception in as a part of this visualization design. But let's come to the part which is perhaps the most interesting one, or most recent one, and that's where the human is the part of this is shaping the visualization design by his own performance of how he or she can infer information from the visualization. So here I basically want to say that the human is part of this redesign in order to create this match between the intended information which wants to be communicated and the insight which is being gained from the visualization. We have done it on a simple scenario where the visualization goal would be to understand the shape of certain structure. So we have been using a particular shading model, which was a Lambertian shading with a little bit of these chromatic shadows added. This was cool to warm shading in order to have it a little bit more stylized, and we performed this gauge figure task again on this data set. And not only us did that, but also people before us. What we looked at was what is the performance of the user to understand the slant and the tilt of the normal, which is being specified by the viewer. The slant is the information. If I have an object in front of me, now the slant would be 0 if the normal will be pointing towards me, and if the normal will be on the contour, the slant would be 90. And the tilt is going from 0 to 360. So we were interested in the slant, because from the previous study, Chromatic Shadows, we have seen some weird pattern in the statistics when we were evaluating it, but there seemed to be some systematic error. And indeed, when we looked at the ground truth slant, which is, we knew the geometry of the structures which we were showing. If we looked at the perceived normal and the ground truth normal, we see that if the human perception will be aligned with this diagonal, then the human perception is just perfect, aligned with the shading model. But here we have seen that it's deviating from the optimum quite a lot, and especially in the area of, let's say, 40 to 70 degrees. So in the slant that would correspond to maybe something between this angle and this angle, this range is perceived badly. So we realize there is a huge error in the statistics. So what can we do? Perhaps we can modify the shading model. How can we modify it? So if it's underestimation, then we over-exaggerate the shading in certain areas. Basically, we over-exaggerate it as big as the error was, the amount reciprocally or proportionally, we will exaggerate these angles. So we created from the original shading model, which was of imperative character, it's a Bayesian shading model with some stylization. We have added a declarative layer, which was not a part of an algorithm, it was just part of statistics gathered from the perception of the user. And here, this information after the first iteration, we have ended up with this shading model, which was communicating the shape hopefully better. The question is, how can we correct the error in such a way that in the next stage the performance will be better? If we assume a linear behavior of human perception, then we can do something, but well, that would be quite naive to think that humans are very linear in perception. So in the first stage, we evaluated the error after the first stage, which is this curve, which is first an overestimation slide in the first stage and underestimation as you have seen it. And in the second stage, we had overall underestimation, but which was lower than in the previous case. So in the first iteration, we improved the situation on average, let's say, but things were then constantly underestimated. And therefore, we have created another iteration, which hopefully was reducing this underestimation and coming closer and closer to the optimal match between the distal and the proximal stimulus in the language of psychologists. Here we can see how this iterative redesign is changing the visualization design on this gecko data set, where we can see that the structures are becoming kind of more pronounced. Just a short outlook with Osmond, we have been working on performing some redesign in motion visualization. If you have a motion of particles and you would like to communicate by the motion certain velocity, then how would this be? Would we just from the motion be able to infer the speed, or the relation between in one area the speed is faster than in another area? Can we tell that this is 5 times faster than another reference speed? That was the subject of our study, and also it was motivated because we wanted to create so-called motion table, or if you have a color legend, that this would be a motion legend. Whether we can, if we have just a subset of motions encoded in this dynamic legend, if we are able to estimate what is in between them, how would we be in interpolating between these stages? So we were motivated to find out how good we are, and in case we are not so good, maybe we can create a compensation model where the speeds will not correspond to the reality, but the speeds will be perceived in such a way as it was intended to be perceived. How much time do I have, Julius? Okay, well then that's fine. So we were interested in different stimuli. We have here always a reference motion, and here we have the test motion. And the question was, how much faster is the one over the other? You basically say the multiplier, 5 times faster, 2 times faster, and so on. And what we were modifying were the speeds of this base speed, for example, orientation. So the global scale would be how fast are these speeds totally. Yeah, we can have an interval of speeds which we perceive, and some speeds are slow, and on the other end there are high speeds. And if we are on this edge, on this end, with both of this, that would be the global scale of velocities. How good we are in this perceived speed interval. That was one question. Another question was, if we have different directions of the velocity of the flow, can we still combine it? Can we tell whether this is faster or slower, even if it goes that entirely other direction or even opposite directions? Then previous literature was claiming that there was also, so representation was of our interest. Are we just having dots, or if we add some features to the elements, particles, will we have a better perception? And that was also a question which we are raising and then studying in our task. And also the contrast, only luminance only versus chroma only, for example. I don't know whether you can see, but this dirt here, that's the elements which should be perceived. And the task was on a regular screen, not on a projector, whether we can perceive the speeds well under different conditions. Previous literature was saying that no, we are not. The contrast in chroma and the contrast in luminance, you are perceiving the speed of chroma slower. Well, we performed a series of tests, and this test didn't confirm at least this fact, which is interesting. Okay, I'm not going further into the evaluation because this is work in process. But our aim was in a different domain, not in the shape, but in motion, to infer maybe something like now we have this perceptual color space, right? We would like to have a perceptual motion space where these different dimensions, like the direction, contrast type representation, are in orthogonal to each other, and we are having a deformed motion model from the ground, from the real motions, which is then perceived in a linear fashion. Yeah. So keeping the human in the loop would be useful, and I'm maybe showing topics from scientific visualization. In information visualization, that would be also quite relevant. And I'm just taking some elements which could be used in information visualization, like for example the software called Gapminder. This software was resonating. The author Hans Rösling was showing on the TED Talks how the world is changing based on showing motion of circles on the screen, and these circles were becoming bigger and smaller based on the development. Certain how poor is the world, the poverty was his topic. Yeah? And over the time, he was showing how these circles were moving in some kind of a 2D scatterplot, and how their size was changing, which was another dimension he was encoding. So obviously, size of, for example, circle is a relevant question to guess. Yeah, and of course we can always write a number and then we know it. But sometimes we are constrained that we will overpopulate the visualization by numbers, and we have just these visual elements. So the question on you here, typical optical illusions question: which circle is bigger? What do you think? Is the white circle bigger? Who thinks that the white circle is bigger? Are they the same? Who thinks they are the same? Okay. And who thinks that the black circle is bigger? So essentially, everybody thinks that they are the same. Probably also because the previous tests were always like, they are in fact the same, but they do not look the same. But actually, they are not the same. And if I looked at these circles previously, I had the feeling that the white one would be the biggest one. But so obviously, we have some problems in guessing sizes, and it depends on where this circle was, what was the contrast to the surrounding, and so on. Vision scientists are interested into that. We can be also interested in this, but our primary concern doesn't need to be why. Why is this like this? Why the neurons are firing in the wrong way? That we do not need to answer, but we have to make sure that we have a good evidence that our visualization design is the best, or we can quantify at least the quality of the visualization design. I think that's the role of visualization researchers. So performing such tests is I believe necessary, but not for the same purpose as vision scientists would do it, for a different purpose, but of course related. So, and when I was looking at this feedback loop mechanism, which is obviously going on here in these two scenarios, which I at least has shown you, it reminds me from my early studies, which I didn't enjoy that much because I was not so much excited about it, but I still luckily remember that the automation, the process, the science of process management has come up with some mechanisms how to deal with systems which should autocorrect themselves out after a certain time. And here we can see this feedback loop mechanism where we have certain system, which would be our visualization design. We have a sensor, which will be our user group and the study, the task. And then we have a controller. And this controller is modulating the input parameters to the system in order to get the best, to get the desired performance. So, and my question would be, can we learn something from the process automation research? Maybe we can find interesting parallels. In this feedback loop, there was this PID controller. So the P was just scaling of the signal. I was the integrative. It was integrating information. The D was the derivative aspect. So this, and you had three coefficients. How much these three aspects, how much should they affect the new parameters which go into the system? Can we just use this PID concept in this feedback loop mechanism? Because the essential question is, how should we, in the next iteration, change the visualization design automatically? It would be good if we do not need to sit and propose some scheme how to do the next iteration. If the system can self-learn that which way to go, which way to improve the visualization design, that would be fantastic. So I was trying to kind of embed into the automation feedback loop this our visualization pipeline, and here we can see that the acquisition filtering is the input, and we have here most of the part of our visualization pipeline, and here we have the test and analysis. However, with this controller, I still do not know what to do there. And maybe if you have good ideas, what would be whether we can just mimic the automation science, whether this is a good idea or not. Maybe you can give me some of your opinions on that. Well, I have a pretty good good idea how we can, what should we do in the sensor part. And that is, we can survey the user. We have a lot of surveillance mechanisms these days, exciting, eye tracking, pen tracking, so you can write on a natural paper and still the positioning is tracked. You don't need to write on the tablet. EEG, all this could be used to survey the user. We have other, so then we have this could be in the controlled study scenario. Then we have crowdsourcing as an opportunity to use. Then we have a statistical analysis, which we can use also as a tool to analyze the user's behavior. But we have also one problem, and that is the individuality is a reality. we have different systems. I was expecting that in this psychophysics task, which circle is the biggest, there will be a group of people who will say, well, I think the yellow is biggest one, or that it will be distributed. It was not, but at least I was thinking that the white one was the biggest one. So I think that making a user which is the normalized user, you know, the average user, it's a question how much sense it makes, because what about these outliers? Should we just ignore them? Well, we will create the visualization system which will be worse than what they already have on the market, and well, we can save our effort. So that's a problem. Okay, what does this mean here? Do you know CAPTCHA? This system for what is this CAPTCHA for? Do you know? How many people know what is it for? Okay, so it's it's a Turing test essentially. Is it a machine or is it a human who is looking at this web page? But do you know what is the difference between CAPTCHA and reCAPTCHA? How many know? Yeah, you don't count. So there is a huge difference, and the difference is that this reCAPTCHA is a very invisible digitization process. You have maybe realized that you have actually two words which you have to write. And the two words mean that if you write these two words, while the first one is the known to the system, and if you write it correctly, then there is assumption that the second one you write is also correct. But this one, the system doesn't know. It's one word from digitalization process of all books, and you are, by entering certain website, by authorizing yourself, contributing to digitizing all books without even knowing about it. So, and this, I think, is a wonderful idea that, well, you need to serve this purpose anyways, but can we have something like that for the visualization? Can we have the read-gauge figure task, where we will authorize ourselves on the web pages just by placing this gauge? And by that, we can have maybe old photographs of old cities or paintings, and people basically could create 3D models just by placing this gauge figure task. So, and we can also that could be one outcome. Another outcome could be that we will know what is their perceptual quality, because we will always have this test scenario next to it. Yeah, Julius, I'm late, I know. But what I also wanted to say that if we can now survey so well the user of visualization, maybe we do not need the algorithm for visualization to be created at all. Maybe it could be an illustrator who trains the system, and then the system will just show the illustration as an outcome of novel objects, not of those which the system has been trained on. Imagine that we just survey an illustrator with eye tracking, EEG tracking, pen tracking. We've drawn with statistics the relationship between the geometry which is drawn and what has been shown. We consider as an entire process of creating the illustration, not as only the final snapshot. Then I think we could reach the state where we can, by statistical analysis, create novel illustrations trained by actual hand-drawn illustrations. And then we do not need visualization algorithms at all, because we have a visualization statistics, so to say. So we can make the visualization less algorithm-based, but more data-driven or more declarative in coming back to the same word. So I wanted to talk about these different patterns, these different opportunities. Each has a good reason to use. At the beginning, direct volume rendering will be not invented if we will be thinking about the goal perhaps so much, and some things have to be technologically driven, not intent driven. But we have always set what we can use. And that's the message which I wanted to tell you today.